Hello friends, in this video I'd like to solve the following problem from the Canadian Mathematical Olympiad 1997, problem number 1. Find the number of pairs xy of positive integers such that the following three conditions are satisfied. X is less than or equal y, GCD of x and y equals 5 factorial, and LCM of x and y equals 50 factorial. So my hints for this problem: first of all, try eliminating this first condition by considering the case, can x be equal y, and can the other two conditions be satisfied at the same time. Then write x as GCD times some number and y as GCD with times some number, and these two numbers a and b should be co-prime. And finally, think about how many prime factors does 50 factorial have. So give this problem a try and I will see you in a minute. So first of all, note that if x equals y and GCD of x and y equals 5 factorial, then obviously LCM, least common multiple of these numbers, cannot be equal 50 factorial, because if numbers are the same, GCD of them and LCM of them are the same. And that allows us to do this nice trick, namely the cardinality of our set. So cardinality of this set running out of space. Well, it's just 1/2 the cardinality of the set with first condition omitted. Why is that? Well, because of symmetry. We see that these two conditions are symmetric with respect to x and y, and there is no middle ground in here. X cannot be equal y, so we have changing x and y gives us the same number of pairs. Okay, so now let's tackle this problem. How many pairs of numbers x and y satisfy these two conditions at the same time? So let's write that x equals 5 factorial times some number, y equals 5 factorial times other number, where a and b are positive integers, and moreover they are co-prime. Then the first condition, namely this condition, is obviously satisfied. So we need only check the second condition. And now, if I write it like that, we see that LCM of x and y, it's just a times b times 5 factorial, and that should be equal 50 factorial. So in other words, a times b equals 50 factorial over 5 factorial. Okay. Now, let's see how many prime divisors does this number have. Well, primes up to 50 are the following. I have prepared my list in advance. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. How many in total? 3, 6, 9, 10, 12, 13, 14, 15. 15 primes. And now let's notice that that means that 50 factorial over 5 factorial will be 2 to some power a is used, alpha, let's say alpha 1, times 3 to some power alpha 2, 5 to the power alpha 3, 7 to the power alpha 4, and so on, 43 to the power alpha 14, 47 alpha 15, because we have 15 primes. And let's notice that all of these numbers, all of these exponents are positive integers. Are some positive integers. In fact, it's not that hard to find their exact values, but it's not necessary, so let's keep it simple. Okay, the only problem may be why alpha 1, alpha 2, and alpha 3, why are they positive? Well, it should be obvious that in 50 factorial we will have a bunch of 2's, a bunch of 3's, and a bunch of 5's in the decomposition. And in the decomposition of 5 factorial we will have much less. So in fact these exponents will be positive. And now let's think about it. A and B should be co-prime. That's crucial. That's crucial. How many ways are there to choose two numbers, A and B, which are co-prime, such that A times B equals this product? How many ways are there? Well, think about it. Let's take our first factor. It cannot happen that 2 to some exponent will go to B and 2 to some exponent will go to A, because that would mean that 2 divides both numbers, and that's against our condition that GCD of A and B should be 1. So either entire number 2 to the power alpha 1 must go to A or must go to B. So let's write it, because it's crucial. It's combinatoric reasoning. 2 to the power alpha 1 must happen in prime, maybe must appear, that's right, must appear in prime factorization of either A or B, but not both. So we have two ways. This number can either go to A or to B. The same happens here. 3 to the power of alpha 2 must appear in prime factorization of either A or B. Again, two ways to choose. We choose A and B, A or B. And that repeats itself. This number 5 to power alpha 3 also must happen either in A or in B. So all in all, the number of pairs A and B, which are positive integers, such that they are co-prime, and their product equals 2 to the power alpha 1, 3 to the power alpha 2, and so on, that must be 2 to the power 15. 2 to the power 15. Maybe let's write it in this line. 2 to the power 15. Okay, and that means that, remember, it's the same as the cardinality of this set right here, the same. And so we have to find the cardinality of set which we are interested in. We just have to divide by 2. Just divide by 2. So cardinality of this set equals 2 to the power 14. And that is our answer. How many pairs are there? 2 to the power 14. That's how many. Okay, so thank you for watching, and I will see you soon.